Спасибо. Today we continue our discussion of tensor products of C-star algebras. So let's recall that what we want to do is to define a C-star norm on the tensor product of two C-star algebras. That is, we want to define a norm which is submultiplicative and satisfies the C-star axiom, and such that the involution is isometric. So in general, the resulting algebra is not necessarily complete, but we can always take the completion and to obtain a C-star algebra. And let's recall that at the end of the previous lecture, we have already considered a special case, which is rather simple but important. This is the case where one of the algebras is the algebra of n by n complex matrices. So in this case, the tensor product is just the algebra of n by n matrices with entries in A. And we explicitly constructed a C-star norm on this algebra. And it's a simple exercise to show that this C-star norm is actually unique, and it makes this algebra into a C-star algebra. So in this case, there is no need to take the completion. It is already complete. And the C-star norm is unique. There is a unique C-star norm on this algebra. By the way, let's recall that the construction of the C-star norm essentially involved the existence of a faithful star representation of the algebra A. That is the second Gelfand-Meinbach theorem. So our next goal is now to extend this construction to arbitrary C-star algebras. And before we can do it, let's make a short digression into functional analysis, and let's discuss tensor product of Hilbert spaces. Tensor product of Hilbert spaces. The construction of the Hilbert tensor product is quite simple. Namely, we have the following proposition. You will have two inner product spaces, H1 and H2. At this point, I don't assume that they are complete. So just vector spaces equipped with inner products, that is, so squalinear Hermitian positive definite forms. Then there exists a unique, there exists an inner product on the tensor product H1 tensor H2, uniquely determined by the following formula. So the inner product of two elementary tensors, x1, y1, and x2, y2, is equal to the following number. We take the inner product of x1 and x2, and then of y1 and y2. Well, the construction of this tensor product is quite simple. I'll not explain you all details of the proof, but the construction is rather straightforward. If we consider it the real case, the case of inner product spaces over the real field, then everything is absolutely straightforward, because in this case, the inner product is bilinear. In our case, it is sesquilinear, but we already know that to deal with sesquilinear maps, it's useful to use the operation of taking the conjugate vector space. So what we want to do is to define an inner product, and a sesquilinear form on this space is nothing but a linear functional on the following tensor product. So we take this space, we take the tensor product by the conjugate space, and linear functionals on this space are nothing but sesquilinear forms on H1 tensor H2. And now we use the fact that the operation of taking the complex conjugate commutes with tensor products. We have already used this fact when we defined the involution on the tensor product of two star algebras. And then we interchange these two factors. So we get H1 tensor H1 conjugate tensor H2 tensor H2 conjugate, and then I put brackets in this way, and I simply apply the inner product here and the inner product here. So we get the following map, which takes this space to the complex numbers. Now this is exactly the sesquilinear form we are looking for. It satisfies this condition. Of course, we also have to show that it is a positive definite and non-degenerate. This is a rather simple and short calculation which involves orthonormal families. By the way, let's observe that the norm that we've just constructed, so we constructed an inner product on this space, and of course an inner product generates a norm in the standard way. So let's observe that this norm has the following useful property. So this is true for every x in H1 and y in H2. This is immediate from this formula. So norms on tensor products satisfying this condition are called cross norms. The respective norm on the tensor product is a cross norm. And I'd like to stress that this property doesn't determine the norm uniquely. In general, there are many different cross norms on the tensor product of two normed spaces. This is only one of them. And there is a whole deep and interesting theory of tensor products of Banach spaces and more generally of topological vector spaces. This theory was created mostly by Grothendieck when he worked in functional analysis. Before moving to algebraic geometry, he has made many important contributions to functional analysis. So one of them was his theory of tensor products of normed and topological vector spaces. Okay, so in general, this tensor product is not necessarily complete for this norm, but again, we can always take the completion and to obtain a Hilbert space. So by definition, the Hilbert tensor product of two Hilbert spaces, and H1 and H2 is the completion of the algebraic tensor product with respect to the inner product given by this formula. And we'll use the following notation for the Hilbert tensor product, denoted by the following symbol. So we use the usual symbol for the tensor product, and we put the dot over the symbol in order to distinguish between the algebraic tensor product and the Hilbert tensor product. Let's look at some concrete examples of Hilbert tensor products. Examples and exercises at the same time. First of all, if we take any Hilbert space H and take the Hilbert tensor product by a finite dimensional space, Cn, then the resulting space is unitarily isomorphic to the Hilbert direct sum of n copies of H. So in all these examples, the isomorphism sign means a unitary isomorphism. So they are unitarily isomorphic. This is very easy. In fact, this observation can be extended to an arbitrary number of copies of the complex of the one-dimensional space. So more exactly, if we take any Hilbert space and consider the Hilbert tensor product by the little L2 space over any index set I, then what we get is the Hilbert direct sum of many copies of H. So here H, every Hi is equal to H. This space can also be denoted by L2 of IH for the obvious reason. So it is defined in exactly the same way as the usual little L2 space, with the only difference that the respective square summable families are not complex valued, they are H valued. So this is the space of all square summable families of elements in H. Of course, if I is finite, then we come back to example 1. And another important example 3, if we take two measure spaces and consider the respective big L2 spaces, L2 of x mu and L2 of y nu, then their Hilbert tensor product is unitarily isomorphic to L2 over the product x cross y. And the isomorphism is quite explicit. If we have an elementary tensor here, then it goes to the function h on x cross y, given by the following formula. Okay, so now it's natural to ask, is it true that the Hilbert tensor product can be characterized by a suitable universal property, similar like in the case of the algebraic tensor product? Here the answer is yes, but at the same time, the class of bilinear maps, which can be factorized, linearized through the Hilbert tensor product, this class is quite exotic. So such maps are called weak Hilbert-Schmidt bilinear maps. So in summary, the universal property of the Hilbert tensor product exists, but it is not very useful. However, what is really useful is the fact that the Hilbert tensor product is functorial. So we have the following proposition. Suppose we have four Hilbert spaces, H1, K1, H2, and K2, four Hilbert spaces. Then I claim that for every, if we have about two bounded linear operators, a bounded linear operator S, which acts from H1 to K1, and a bounded linear operator T, which acts from H2 to K2, there exists a bounded linear operator, which will be denoted like this. So it acts from the Hilbert tensor product of H1 and H2 to K1 tensor K2. And this operator is uniquely determined by the following simple formula. It takes every elementary tensor, x tensor y, to the elementary tensor sx tensor t y. And moreover, the norm of this operator, is equal to the product, the norm of S times the norm of T. So this result readily implies that the Hilbert tensor product is a functor in two variables. So what is also useful is that if we consider the following linear map, so we can take the space of bounded linear operators from H1 to K1, the space of bounded linear operators from H2 to K2, we can now form their algebraic tensor product. And consider the map from this algebraic tensor product to the space of bounded linear operators between the Hilbert tensor products H1, H2, K1, K2. So this map takes every elementary tensor A, S, tensor T to the respective operator given by this formula. So clearly the existence of such a map is immediate from the universal property of the algebraic tensor product. And what I claim here is that this map is injective. This map is injective. Basically, this map is a Hilbert version of the well-known algebraic map, which is usually called the home tensor interchange. So it is injective. Well, just a few words about the proof. To prove part one, first of all, we clearly can define this map on the algebraic tensor product in the obvious way. And so now the only thing we want to prove is that the respective map between the algebraic tensor products is bounded for the norm generated by this inner product. But this is again a short and elementary calculation which involves orthonormal families. So it turns out to be bounded, and therefore we can uniquely extend it to the completion. And we get the map between the Hilbert tensor products. And again, this equality is proved by a short and elementary calculation. The injectivity of this map is a pure algebraic fact. Actually, it holds at the level of vector spaces and linear operators between arbitrary vector spaces. So part two is a simple exercise in linear algebra. Okay, now we can define tensor product of star representations. So we have the following proposition. Suppose we have two star algebras, and two star representations. Say pi is a star representation of A on the Hilbert space H, and tau is a star representation of B on another Hilbert space K. Star representations. Then, first of all, there is a star representation of the tensor product of A tensor B. So at this point, we consider this algebra just as a star algebra. So we don't assume that A and B are equipped with a norm. They are just star algebras. So this is also star algebra. And there is a star representation of this algebra, which will be denoted like this, pi tensor tau. And it acts on the Hilbert tensor product, H tensor K. And this representation is uniquely determined by the following formula. It takes every elementary tensor, A tensor B, to the operator phi of A tensor tau of B. So this operator exists by part one of this proposition. This is an operator on H tensor K. And moreover, if we know that both pi and tau are faithful, if pi and tau are faithful, then so is their tensor product. Well, here I'm happy to give you a full proof because it is just a line. So we take the tensor product of A and B and consider the tensor product of pi and tau considered as just as linear maps. So this map acts from this tensor product to the tensor product of B of H and B of K. This is just the algebraic tensor product of pi and tau. And now we simply combine this map with the map from part two of this proposition, so which gives us an inclusion of this algebra into B of H tensor K. This error is easily seen to be a star homomorphism. So if now compose these two maps, we get exactly what we need. And the same diagram shows that if pi and tau are faithful, then so is this map, because in this case this is injective, this one is injective, and this one is always injective by the previous proposition. So this is a faithful star representation. Okay, now we are ready to define, let's come back to C-star algebras. Now we are ready to define a C-star norm on the tensor product of two C-star algebras. The respective norm, the respective tensor product is usually called the minimal or the spatial or minimal tensor product of C-star algebras. So suppose we have two C-star algebras A and B. A and B are C-star algebras. And let's take their universal representations, omega A and omega B, respectively. Their universal representations. By definition, the spatial or the minimal C-star norm on the tensor product of A and B is defined as follows. So we take an element in the tensor product, we apply the tensor product representation, omega A tensor omega B, we apply it to U, we get an operator, and we simply calculate the norm of this operator. And this is a C-star norm on the tensor product. Why is it a C-star norm? Well, it is a C-star norm by the previous proposition, because this representation omega A and omega B are faithful by the Gelfand-Naimark, by the second Gelfand-Naimark theorem. This one is also faithful, so it is indeed a C-star norm. Not just a semi-norm, but indeed a C-star norm. The Russian for spatial is пространственное. Spatial means пространственное. So it's more or less clear what it is called spatial, because it involves two concrete Hilbert spaces, namely the spaces for the universal representations of A and B. And why it is minimal? Well, I'll explain this in a few minutes. By the way, let's also observe that this norm is also a cross norm. If we take an elementary tensor on in the tensor product, then we have the following equality. This is immediate from the definition of the respective norm and from this equality. In general, this algebra is not necessarily complete, but we can always take the completion, and the completion is called the spatial or the minimal C-star tensor product. The completion of a tensor D with respect to this norm is called the spatial or minimal C-star tensor product. Of A and B. And we will use the following notation for this tensor product. we'll denote it either like this, or sometimes I write min here as a subscript to the tensor product sign. Actually, in the sister algebra literature, it is common to just to write the usual sign of the algebraic tensor product without any other subscripts or superscripts, and to say that, well, this sign will always denote the minimal sister tensor product. Sometimes this leads to a confusion, because sometimes we have to consider the algebraic tensor product as well. Let's try to use a more complete notation for this tensor product. Okay. Well, the definition is short, of course. The definition is very short, but it has two serious disadvantages. First of all, it is practically incomputable in the sense that, well, it involves the universal representations of A and B. And the universal representation of a sister algebra is something really huge. Let's recall that it is defined to be the Hilbert direct sum of all GNS representations taken over all states. So this is something very big, and it's impossible to describe it in reasonable terms. And the second disadvantage of this construction is that it looks non-functorial. However, we have the following important result due to Takesaki. By the way, the theory of tensor products of sister algebras was the foundations of this theory were essentially created by Takesaki in the 1960s. So suppose we have two sister algebras, A and B. Then, first of all, we have the following alternative formula for the minimal or spatial sister tensor norm. That is, for every element U in the algebraic tensor product of A and B, the respective norm is equal to the supremum of the norms of operators pi tensor 2 applied to U, where pi is an arbitrary star representation of A, and 2 is a star representation of B. Well, formally, of course, the class of all star representation is not a set, but it's rather easy to make perfect sense of this supremum. That is, this means basically that for every pair of star representations, pi and 2, of A and B respectively, this number is less than or equal to this one. So the supremum is attained at the universal representations of A and B. Another useful formula for the same norm is as follows. So suppose we have two star representations, pi and 2, of A and B respectively, which are faithful. Pi is a faithful star representation of A, and 2 is a faithful star representation of B. Faithful star representations. Then, for every element U in the tensor product of A and B, the spatial C-star norm is equal to the norm of the following operator. So in other words, there is no need to take the universal representations here. We can take arbitrary faithful representations of A and B, and they give the same number. Why is it useful? It is useful because for many concrete sister algebras, there are some very natural and manageable faithful representations which are different from their universal representations. And so this enables us to calculate the sister norm in a rather elementary way. And part 3 explains why the minimal C-star tensor product is so called. So for every C-star norm, on the algebraic tensor product of A and B, we have the following inequality. The spatial norm is less than or equal to any other C-star norm. So it is literally, it is minimal in the class of all C-star norms on the tensor product. The proof is not trivial at all. Let me just give you a few ideas. To prove part one, we have to show that for every pair of star representations, pi and 2, this number is dominated, is less than or equal to this number. So to prove this, first of all, we decompose pi and 2 into cyclic summands. A cyclic representation is a representation which is essentially generated by a single vector. And it's rather easy to show that every star representation can be decomposed into the Hilbert direct sum of cyclic representations by using Zorn's lemma. And then we have to observe that every cyclic representation is actually isomorphic to a suitable GNS representation. And now, by using this fact, we deduce that this norm is less than or equal to this one. Part 2, the proof of part 2 can be either reduced to part 3, or it can be proved independently by using suitable finite dimensional approximations. Here, the result that the norm on the tensor product on this algebra is unique. The uniqueness of the C-star norm on this algebra is quite essential in the proof of part 2. And part 3 is rather hard. Surprisingly, it's rather hard, and it involves some basic facts in representation theory of C-star algebras that, unfortunately, we don't have time to discuss such facts. Okay, so why is this result useful? Well, I have already explained why part 2 is useful, and part 1 is useful because it readily implies that the tensor product is functorial. Corollary 1. You will have two star homomorphisms between C-star algebras, say phi from A1 to B1, and psi from A2 to B2. They are star homomorphisms between C-star algebras. Then there exists a star homomorphism, phi tensor psi, between their spatial tensor products, A1 tensor A2 to B1 tensor B2, uniquely determined by the following formula. Takes every elementary tensor, A1, A2, to phi of A1, tensor psi of A2. Well, indeed, first of all, we define this map on the algebraic tensor product, which is quite straightforward. So it acts between the algebraic tensor products of A1, A2 and B1, B2. And then we have to show that it is bounded for the respective spatial C-star tensor norms. So, and the boundedness can easily be deduced from this formula. So the spatial tensor product is functorial. Corollary 2. So corollary 1 follows from part 1 of this theorem, and corollary 2 follows from part 2. If we have two Hilbert spaces, H and K are Hilbert spaces, and suppose that we have two C-star subalgebras of B of H and of B of K respectively. C-star subalgebras. Then their spatial tensor product, A tensor B, is nothing but the closure of the algebraic tensor product in the space of bounded, in the algebra of bounded linear operators on the Hilbert tensor product, H tensor K. This really follows from part 2. Just take inclusion maps of A into B of H and of B into B of K, and we get this formula. Here is a useful special case, corollary 3. This is a special case of corollary 2. Here we have two Hilbert spaces, say H1 and H2. Then the spatial tensor product of the algebras of compact operators on H1 and H2 respectively is nothing but the algebra of compact operators on the Hilbert tensor product. So here the only thing to show is that the algebraic tensor product of this algebra by this algebra is dense in here. But the density can be proved by using finite rank operators. It's a standard fact that every compact operator on the Hilbert space can be approximated by finite rank operators. And this easily implies that the algebraic tensor product of these algebras is dense in here. So now applying corollary 2, we get this isomorphism. By the way, if we replace here compact operators by bounded operators, then the result is not true. This tensor product is something which is strictly smaller than, so it is, of course, it is included in the algebra of bounded operators on the Hilbert tensor product, but they are not the same if the spaces are infinite dimensional. Another important special case is the case where one of the algebras is commutative. Let's introduce some notation. Suppose we have a locally compact Hausdorff topological space X. And a sister algebra A. In this case, we can introduce the following algebra, which will be denoted by C0 of XA. So this algebra consists of all continuous functions f from x to a, such that the norm, that is the function which takes x to the norm of f of x, vanishes at infinity. So in this case, we can say that f itself vanishes at infinity. Well, it's a simple exercise to show that this is a sister algebra. The involution is given by the following formula. So we simply apply the involution pointwise. And the norm is just the supremum. The norm of f is the supremum of the norms f of x, where x runs over our space. Now we have the following result, proposition. There is an isometric star isomorphism, as denoted by phi, between the spatial C-star tensor product of C0 of x and A, and the algebra C0 of XA. This isomorphism is uniquely determined on elementary tensors by the following formula. It takes f tensor A to the function which takes x to f of x A. Well, let me give you a short idea of proof. Just the construction which implies the existence of this isomorphism. The idea is to take a very concrete faithful representation of C0 of x. Let's denote it by M. So it takes C0 of x to the algebra of bounded operators on the Hilbert space little L2 of x, of square summable families over x. And this representation takes every function f to the multiplication operator mf, where mf of g is just the pointwise product of f and g. And this is a faithful star representation. Next, we take an arbitrary faithful star representation pi of A on the Hilbert space H. And we combine these two representations into a representation of this algebra of A-valued continuous functions. Let's denote this representation by m pi. So it acts on the Hilbert space L2 of xa, of xh, of square summable families over h indexed by x. And this representation acts as follows. If f is an A-valued function on x, then m pi of f is an operator on the space. So it if we apply it to a function g from x to h, we must get again a function from x to h. And this function is defined as follows. First of all, we calculate f of x. This is an element in A. Then we apply pi, and we get an operator on h. And we apply this operator to g of x, which is a vector in h. So the resulting element sits in h. And it can be shown that this map is well defined, and it also gives us a faithful star representation of this algebra. And these representations are related to each other by the following diagram. So here we take the algebraic tensor product of C0 of x and A. So the spatial tensor norm on this algebra is defined in terms of representations of the representations m and the pi. And so this representation acts on L little L2 of x tensor H. Identified with the space L2 of xh. So we have, as a result, we have an isomorphism between these two algebras. And here we have m pi. And the simple calculation shows that the diagram is commutative. So as a result, the spatial tensor norm on here, which is induced from this algebra by means of this arrow, is nothing but the operator norm induced from here on this algebra with respect to m pi. So as a result, this arrow is isometric for the minimal, for the spatial tensor norm on here, and for the supremum norm on this algebra. And so finally, we have to show that it has dense range. But the density of the range follows from some partition of unity argument. So as a result, it uniquely extends to an isometric star isomorphism. So is it okay? I'll try to check this because there were some sounds in here. It seems that I have to change the battery. Что-то она мигает батарейкой. Это она, я только не очень понимаю, к какой батарейке это относится, к той, которая тут, или к той, которая в микрофоне. Вон, видите, мигает. Это самое, это подключена, сама камера. Ну, вроде, да. Может, это тогда к этому относится? А? О. but can you hear?
Yeah, I have sound.
Okay, let's continue. I hope.
Я думаю, он просто жалуется, что нет карты памяти.
Это, ну тогда ладно.
Карта памяти нам не нужна.
Хорошо. Okay, let's continue. Let me now say a few words about another version of C-star tensor products, namely the maximal tensor product of C-star algebras. So again, we suppose that we have two C-star algebras, A and B. Let's recall one of the formulas which defines the minimal C-star tensor norm on the tensor product. So this is the supremum over all pairs of representations pi and 2 of A and B respectively. So pi is a star representation of A, and 2 is a star representation of B. This is true for any element U in their algebraic tensor product. And now we have the following definition: the maximal C-star norm on the algebraic tensor product is given by the following formula. It is also a suitable supremum, but the difference is that now we consider all representations of the tensor product and apply them to U. So here pi runs over the class of all star representations of A tensor B. So what's clear from this definition? It's clear that the maximal C-star norm is greater than or equal to the minimal C-star norm. Because here we consider all star representations of the tensor product, and here we consider only those which come from a pair of representations of A and B respectively. What is not clear, however, is that this supremum is finite. Well, it is indeed finite, and we have the following result. The theorem. First of all, this number is indeed finite for every U in the tensor product. And this implies that this is indeed a C-star norm. A C-star norm on the tensor product. This fact is rather trivial in the case where the algebras are unital. So you can try to prove it as a simple exercise. Basically, the idea is that if A and B are unital, then both A and B become subalgebras in the tensor product in a natural way. And so if we have a star representation of the tensor product, we can simply restrict it to A and to get a representation of A, restrict it to B and get a representation of B. And we know that every star representation of a C-star algebra, the norm of every star representation is exactly 1. And this easily implies that this number is finite. But if A and B are not unital, then the proof is surprisingly non-trivial. And as you might expect, it involves approximate identities in C-star algebras. If A and B are not unital, then in general, A and B are not subalgebras in the tensor product. There's no natural inclusion map. So that's the problem, but fortunately the result is true. Second,
То
C-star algebras.
No, A tensor B in this definition.
Well, we assume from the very beginning that they are C-star algebras.
Yes, but the tensor product. We
The-
want to define the.
Here, the tensor product is just, we consider it as a star algebra.
Yes.
It is not a C-star algebra.
Yes, and the representations are in Hilbert spaces.
Yeah.
Okay.
If let's recall once again, if we have two representations, pi and 2, then we have the following picture. So we take the tensor product of A and B as algebras. We take the pi tensor 2, which acts from here to B of H.
No, it's not the first definition. I'm asking about the second.
And the second one, yeah, we consider all-star representation of A tensor B on Hilbert spaces. Yeah. Why not?
Because they. But their representations not in algebraic sense.
They are star homomorphisms from A tensor B to B of H, where H is a Hilbert space. So of course we don't have any norm on the tensor product from the very beginning. So they are just star homomorphisms from A tensor B to B of H, where H is a Hilbert space. Part 2 is about homomorphisms from A tensor B to other C-star algebras. So for every C-star algebra, let's call it C, and for every star homomorphism phi from, let's just consider arbitrary star homomorphism. I don't use any special notation. Every star homomorphism from A tensor B to C uniquely extends to a star homomorphism. It's maybe too early to extend it. What I want to say that it is satisfies the following estimate. So we have the norm of phi of u is less than or equal to the norm of u, where the norm of u is given by this formula. Property 3 is that the maximal C-star norm is actually the maximal one. So for every C-star norm on the tensor product, we have the following inequality. This norm is less than or equal to the maximal C-star norm, which explains why it is so called, why it is maximal. It is maximal because it is literally maximal. And property 4 is that the maximal norm is also a cross norm, similarly to the minimal one. So we have the following equality. So we see that the maximal and the minimal norm are the same on elementary tensors, but in general they are not the same on arbitrary elements. Well, I have already told you something about the proof of 1. It is a simple exercise if the algebras are not unital, and it is quite non-trivial if they are not. Part 2 easily follows from the definition and from the Gelfand-Dynamic theorem. Because if C is the algebra B of H of operators on a suitable Hilbert space, then phi is just a representation of the tensor product, and just by the definition of the maximal C-star norm, we have this inequality. If C is arbitrary, then we just embed it isometrically into B of H by using the second Gelfand-Dynamic theorem, and everything is reduced to the case where C is just B of H. 3 follows from 2. Just consider the identity map from this algebra to itself. First of all, we equip it with the maximal norm, and then with this norm, and apply 2, and we get property 3. As for property 4, it is, again, here the situation is about the same, very similar to part 1. It is very easy in the case where the algebras are unital, and it requires some extra work in the case where they are not unital. Let's look at some simple corollaries. Corollary 1. So for every C star algebra C, every star homomorphism from the algebraic tensor product. Oh, sorry, maybe before discussing corollaries, let's introduce the following definition. So the maximal tensor product, the maximal C star tensor product of the C star algebras A and B is the completion of the algebraic tensor product with respect to the maximal C star norm. And it will be denoted like this. This is the standard notation for the maximal tensor product. So let's now look at two simple corollaries of this theorem. Corollary 1, if we have a C star algebra C, and a star homomorphism from A tensor B to C, this homomorphism uniquely extends to a star homomorphism defined on the maximal tensor product. Uniquely extends to a star homomorphism from the maximal tensor product of A and B to C. This readily follows from part 2. So part 2 shows that it is bounded and its norm is at most 1. So we simply extend it to the completion by continuity. And corollary 2 is actually a special case of corollary 1. The identity map on the algebraic tensor product uniquely extends to a surjective star homomorphism from the maximal tensor product of A and B onto the minimal tensor product of A and B. This is just a special case of corollary 1. We take the inclusion of the algebraic tensor product into the minimal tensor product and extend it to this one. Why is this surjective? Let's recall that any star homomorphism between C star algebras has a closed range. So as a result, the range of this area is closed, but on the other hand, it is dense because it contains the algebraic tensor product. So as a result, it is surjective. An initial question is this map an isomorphism? And this question leads to the following definition, also due to Takesaki. We say that a C star algebra A is nuclear. So the Russian terminology is ядерная. A is nuclear if for any C star algebra B, the minimal C star norm is equal to the maximal one on the algebraic tensor product. So accordingly, this means that there is a unique C star norm on the algebraic tensor product. There is a unique C star norm on the algebraic tensor product of A and B. This is indeed equivalent because we know that the minimal is indeed the minimal one and the maximal is indeed the maximal one. So if they are the same, this means that such a C-star norm is unique. Any other is somewhere in between. So this is equivalent to the uniqueness of a C-star norm. And equivalently, this can be said as follows. This is equivalent to say that this canonical map is an isomorphism. Well, indeed, if the norms are the same, then clearly this is an isomorphism. And conversely, if it is an isomorphism, then it is isometric, because this is an isomorphism between C-star algebras, and so the norms are the same. Actually, we already have an example of a nuclear C-star algebra. This is the algebra of n by n complex matrices. So at the end of the previous lecture, we have already discussed that for any C-star algebra A, there is a unique C-star norm on the tensor product of Mn by A. So it is nuclear. More generally, an example and an exercise at the same time. If A is a finite dimensional C-star algebra, then it is actually isomorphic to a direct sum of finitely many matrix algebras. And by using this isomorphism, it's easy to deduce that it is nuclear. There is also an important result, also due to Takesaki, which states that every commutative C-star algebra is nuclear. Every commutative C-star algebra is nuclear. And this is quite non-trivial. Again, this involves some deep results from representation theory of C-star algebras. Let's now look at something non-commutative. We have the following useful proposition, which roughly means that if a C-star algebra can be approximated by nuclear algebras, then it is also nuclear. So more exactly, we have the following result. Suppose that A is a C-star algebra, and suppose that script B is a directed family of C-star subalgebras of A. Now here, directed, or if you like, filtered, means that if we have two algebras in this family, or any B1 and B2 in this family, there is another subalgebra B3 in the same family, which contains both B1 and B2. Let's also assume that every algebra in this family is nuclear. Suppose that each B in this family is nuclear. And suppose that the union of this family is dense in A. I claim that A is also nuclear. A is nuclear. The idea of the proof is rather simple. We take the union of all these subalgebras let's denote it, say, by A0. It is dense in A. Now we take any C-star algebra, say C, and we look at A0 tensor C. By using the fact that every C-star algebra in this family is nuclear, we see that there is a unique C-star norm on this algebra. So there is a unique C-star norm on A0 tensor C, for the simple reason that any element in this algebraic tensor product can be written as a finite sum of elementary tensors, and every elementary tensor sits in an algebra from this family, but the family is directed, so as a result, every elementary tensor in this algebra sits in some B tensor C for a suitable algebra B in our family. But there is a unique C-star norm on this algebra, and so as a result, there is a unique C-star norm on this tensor product. And now by using the density, it's a simple exercise to show that the density of A0 in A implies that the same is true for A tensor C. The same is true for A tensor C. So as a result, A is nuclear. Here is a concrete example where this theorem works. Example. The algebra of compact operators on any Hilbert space is nuclear. Again, basically the idea is to approximate this algebra by matrix algebras. So more exactly for any, we take any finite rank projection, PL, the orthogonal projection onto a finite dimensional subspace L of H. And for every such finite dimensional subspace, we consider the following algebra, which consists of all operators of the following form. Roughly, this is a kind of the upper left corner of the operator T. If we write T as a matrix and as an infinite matrix, then this operator corresponds to this corner. It is finite dimensional, and it is actually isomorphic to the matrix algebra Mn, where n is the dimension of L. And now it's rather easy to prove that by using the fact that this family PL forms an approximate identity in QH. We can show that this family satisfies the conditions of the previous proposition. So all these algebras are nuclear because they are isomorphic to matrix algebras, and their union is dense in KVH. So KVH is also nuclear. On the other hand, there are some non-examples, that is, examples of C-star algebras which are not nuclear. The first such example is again due to Takesaki. If we take the reduced group C-star algebra of the free group onto generators, F2, so F2 is free group onto generators, then Takesaki proved that this algebra is not nuclear. This was an example from our first lecture in C-star algebras. So we take, if we take any group G, we can consider the Banach algebra L1 of G, of summable families on G. And we consider the so-called regular representation, as noted by lambda, of this algebra on the Hilbert space L2 of G, which acts by the following simple formula. Lambda of F is an operator on L2 of G, which acts as a convolution with F. So this is a star representation, and by definition, the reduced group C star algebra of G is the closure of the image of lambda. So this is a C star subalgebra in here, and it is called the reduced group C star algebra. So another version of the group C star algebra is constructed as follows. We consider all star representations of L1 of G and take the supremum of their norms. It turns out that the supremum is finite, and the completion for this for the respective norm is called the full group C star algebra of G. And in general, this one, the reduced one, is a quotient of the full group C star algebra. So Takesaki observed that, if I'm not mistaken, this is 1964. Takesaki observed that this algebra is not nuclear. This is a rather interesting and non-trivial result. Another classical example was obtained by Pirkovski in 1981. Basically, he proved that B of H, where H is an infinite dimensional Hilbert space, is not nuclear. Pirkovski, 1981. Of course, here we assume that H is infinite dimensional. Well, let me say just a few words why nuclear algebras, nuclear C-star algebras are so called, why they are nuclear. They are called nuclear by a formal analogy with the nuclear topological vector spaces introduced by Grothendieck. Grothendieck studied tensor products of Banach spaces and more generally of topological vector spaces, and he observed that on each pair of topological vector spaces we can define two natural tensor products, the so-called projective tensor product and the so-called injective tensor product, which is denoted like this. So if we have two topological, locally convex topological vector spaces, E and F, then we can form the following two locally convex spaces. And there is a natural map from here to here. In general, it is not surjective, and in general, it is not injective. And if it is an isomorphism, if the space E has the property that this is an isomorphism for every F, then E is said to be nuclear. This is only one of many definitions of a nuclear space. There are many other definitions. And one of the most classical definitions of a nuclear space is given in terms of nuclear operators. And this is the reason why Grothendieck called the nuclear spaces nuclear. So they can be defined in terms of nuclear operators. So if you now compare this definition with the definition of a nuclear C-star algebra, we see that they are very similar. Of course, this is only a formal analogy, because here we deal with different types of tensor products. By the way, a C-star algebra, an infinite dimensional C-star algebra, can never be nuclear as a locally convex space, because an infinite dimensional Banach space is never nuclear. So these two types of nuclearity are not compatible, of course. But nevertheless, the formal definitions look very similar. This was the reason why Takesaki called such C-star algebras nuclear. Okay, so it's time to finish. Well, basically, that's all I wanted to tell you about tensor products of C-star algebras. So now I can state that this is really the end of our introduction to C-star algebras. So at the next lecture, from the very beginning, we discuss K-theory. First, for arbitrary rings, we define a functor K0. And then we study some of its basic properties. And then we specialize to C-star algebras. And define K1 and so on. So, well, maybe I'll repeat this once again at the next lecture, but I have already told you at the first lecture that there are two types of K-theory, which are both motivated by K-theory of topological spaces, but which are quite different. The first one is algebraic K-theory, which deals with arbitrary rings, and the second one is operator K-theory, which studies functional analytic objects like C-star algebras and more generally Banach algebras and Fréchet algebras, and so on. So these two types of K-theory are quite different for many reasons, but if we look at the foundations of these subjects, there is an important definition which is common for both versions of K-theory. This is the definition of the functor K0. So the K0 for unital rings is compatible with K0 for C-star algebras. So that's the reason why we define first K0 for arbitrary rings, and only then we'll specialize to C-star algebras and define K1. So K1 for rings and K1 for C-star algebras are not the same. Okay, thank you. So that's all for today.